Okay.
As we're going through, we want to think about what we want to discuss, which we do at every meeting, which is how do we get together to analyze the runs that have already been done, and should there be future GeoMIP experiments for another round? And what should they be? Or should we encourage more people to do the ones that already exist?
And of course, if you have questions or if you want to intervene, you can just raise your hand, since maybe there will be too many to just talk freely, but I will try to check the list of people, and or you can just write in the chat if you notice that we're ignoring you, but I should get it. So
if you're
just
new
raise
to
your hand.
Zoom,
Yeah.
if you're new to Zoom, which is probably not the case, the reactions button at the bottom on the right, you click there and then you can click raise hand.
Yep.
We'll do that for the discussion.
Okay, Doug, I think you can start before Abriel wakes up.
Yep. Okay, so probably everybody knows me, but I'm Doug MacMartin at Cornell. So you're going to see about 3 talks this morning talking about scenario definition. Be very interesting to see sort of what's the commonality and where's the differences in perspectives. And just to point out that there's a bunch of other discussions as well that are not here. So I know, for example, Kate Rickey is working on this, and David Morrow and Tyler are working on this. Other people, there's various other people who are thinking about it as well. When we talk about something being policy relevant, of course, what we really mean is that we're supporting future decisions about whether to deploy geoengineering, and that doesn't just whether to deploy it, but if so, you know, how much, when do you start, how do you do that? So that basically means you can't just think about one scenario, but you have to sort of span at least an adequate range of that decision space, as well as capturing risks like termination. Moving forward, I think it would be very valuable if one could integrate assessments of solar geoengineering along with more regular climate change scenario assessments. So that basically means, of course, branching from standard SSPs, representative of some plausible future. So Glenn's that I've been involved with started in 2020, and not picking a high emissions case purely to obtain high signal to noise. If the purpose is because one wants to understand what happens in high emissions, then run high emissions. But I think there's been a number of cases in the literature where people sort of assuming that something happens about geoengineering purely because of looking at a high emissions case. I think the other just broad context thing is just to be clear about, you know, if our purpose here is running Earth system models, there are lots of, when, you know, if you're just to like go out into the much broader governance, for example, discussions of geoengineering, there'd be all sorts of scenario questions that they're interested in that are not relevant, that basically ESMs are not relevant to answer. So basically issues around chaos associated with deployment. And I would also argue that, you know, it's a very relevant question to think about a overshoot scenario, for example, and how long a deployment might be. But that's, you don't need an Earth system model to answer that question. So I think when one's designing scenarios, one has to be very careful about what's the role. So things that matter, the emissions scenario, where do we think we're headed? Temperature target, or where do we want to go? Start date, strategy, how do we get there? So latitudes of injection, goals, and so forth. And then other things that might happen, so termination, interruption, and so forth. Broadly, we think that roughly speaking, the strategy dimension is separable from the others. So one can basically pick one scenario and explore a strategy, or pick one strategy and explore the others. The strategy dimension would be an entire other talk, so I'm not going to say about that. So we picked a few things and we've started some simulations. So, and I'll define our logic a little bit more at the very end, assuming I have time. So 3 different temperature targets, one representative of 1.5 degrees and the other 2 a little bit cooler, looking at the effect of a delayed start, and then termination and phase out. So far, we've run 1 case each for the different temperature targets. We will run a couple more. And then in addition, NCAR is doing a 10-member ensemble of that blue case, what we're calling our sort of baseline, and we should get simulations of that. Jim Haywood will do some in UK ESM, and Ben is going to do some in GIS as well. So anybody who wants to look at these simulations, just let us know and we can point them to them. And then just in terms, very quickly, in terms of sort of what our rationale was, choice of start date, you know, you could, we don't know when it's going to start, but the research is less urgent for things further out. So we sort of picked the earliest that we thought was sort of likely enough to be worth simulating. Simulation length, long enough to get the regional response, but not so long that we're guessing on what future technology might look like. CO2 molecules do the same thing 100 years from now that they do today, but I have no idea what technologies we might use in 100 years. And the upshot of that is that in picking the SSP, it doesn't actually matter that much over this time frame. We picked SSP 245 because it's roughly consistent with Paris INDCs, and it's a lot more analyzed than some of the others, and I think that's my 5-minute belt, so I'll stop. And happy to take lots of questions.
Thank you, Doug.
Actually, maybe I should keep the share up for questions.
Questions?
So 1 question from Pete and 1 from Claudia.
Hi there. Did you mention what the strategy is in these simulations?
No, I didn't mention it. The ones we've done so far is basically the same strategy that we used in Glenn's. And we have a whole long list of other strategies that we're going to try. It's not obvious to me that the one we used in Glenn's is the best one to be using going forward. But one of the reasons why this is a little bit more exploratory still is in terms of other models is that requires a feedback loop. Yeah. And so there's limited numbers of models. If you're only tuning one thing, you can sort of tune it by hand. But if you're trying to tune injection at multiple latitudes, that's pretty hard to do without an online feedback loop. So we're working with Jim to get that coded in UK ESM, for example. Cool. Claudia?
Yeah, I'm not 100% sure if I agree always with the what you said about not choosing high emission for just to get a high signal to noise ratio, because I think for many points you are right. But if you want to check at whatever, you know, some novel danger which could arise or something special, then it may make sense still. I mean, I think there are still features that we may not have fully explored. So I just wanted to
I'd say not for the purpose of getting a high signal to noise. So if the purpose is to explore something policy relevant, then definitely. But if it's simply like, hey, we're not getting a big enough signal, let's go amp up the forcing.
Well, I mean, if you want to look at something like the possible influence on tipping points or whatever, which are, you know, something where it's hard to get a strong signal, I'm not sure if I mean, maybe it's not the most important thing to discuss.
My answer would simply be run more ensemble members. But that's partly because I've seen too much confusion in people analyzing simulations. But that's a personal view at some level.
Okay, well, still interesting things.
Simone and Alan, I'm not sure who had their hand up first.
Ellen was first.
Okay, Doug, you only talked about using temperature targets. What do you think about using other targets, such as how much food we can produce rather than just temperature?
I think it's a great idea, and I think there's a long discussion to have there. We do have simulations where we've looked at sea ice as the target, for example.
All right, let's discuss it later.
Yeah, I'm not sure I can answer that in like 30 seconds.
Okay.
Simone?
If you go back to your slide with the nice So one thing that is interesting to me is that the green and the pink, they will not sustain the climate, right? You will have to do geoengineering forever in this case. But that's just because the scenario isn't there that would put the emissions down. Is that correct? I mean,
That's
because, yeah.
basically suggesting that under reasonable rates of CDR, the duration of the overshoot is quite long, and that the duration of that overshoot is purely a function of assumptions on CDR rates and peak emissions. And that, so our presumption, and that's a valid point for discussion, is that essentially the regional climate response, the reason for running the ESM to get the climate response is pretty much converged by the time you've run it for this long. And so if the question is how long is the overshoot, you don't need to run an Earth system model to do that.
Well, I'm not so sure about that part either. That's what I wanted to comment to. For this one, so in a way you just want to cool a little bit the climate and then keep it, and basically eventually the amount of geoengineering would get reduced with the CDR that will happen. Is that the idea? But it's not within the time frame that is illustrated.
Right.
Yeah, okay. And yeah, so for the...
But I'm saying that's a separate question.
Yeah, okay. Because for the overshoot, the other thing is that climate variability matters quite a bit, and climate feedback on how long you will have to run it. So I think simple integrated assessment models don't capture that.
Yeah, but neither does our current WACM capture that either, because it doesn't have the carbon cycle feedback.
Yeah, right. So we need better
Okay,
models.
we need to wrap up for the next talk. And then Iris has a question. Iris, I hope you don't mind if we keep it for the discussion part.
Yeah, that's fine, no problem.
Okay, so Andrew, I'll share your screen, your presentation in a second.
I'll just say okay when it's time to skip slides, right?
Mm-hmm.
If you go full screen, that'd be great.
Yeah. Which one am I sharing? Okay, can you see?
You got to
yeah,
flip the view. Swap.
Yeah,
okay, so I had, okay.
Thanks.
Yeah. Okay, go ahead.
Right, it's it's live subtitling, which I've never seen before. That's kind of cool. So could you skip that? So it's title is 18 politically relevant solar geoengineering scenarios. So we're taking a different approach here and concentrating much more on the politics and much less on the detailed instructions for modeling. As you'll see, I'm not going to read out the full author list here, but suffice to say, Simone is also on the call, so I'll have to make sure I behave myself and don't say anything that she might get cross with me for. Okay. So the key points is that the current scenarios are physically impossible or politically unrealistic, and to make politically relevant experiments, we have to look at both desirable and undesirable futures, and making clear, potentially which ones are and aren't desirable, so that we're not coming across as advocates for some of the more dangerous scenarios. And we want to inform the political process first and foremost with this new approach, rather than just testing the models to destruction to see what happens. Okay. So this is, if you can get this concept, then the whole thing will fit together for you. The rest of them are just examples that you can include or exclude as you might wish. But there are the two classes that you've got or two axes are, you've got towards the top of the graph, you've got the more planned scenarios. Towards the bottom of the graph, you've got the more reactive ones, and then you've got a scale differential. On the left-hand side, you're looking at more regional and spatially limited scenarios, and to the right-hand side, you've got more global scenarios. If you think about any scenario that you might conceive of, and then stick it on that axis, you can see if you're populating that space effectively or not. I'll try and rattle through these scenarios as quickly as possible, because you don't need to go into great depth on each of them, but I'll pick perhaps a few examples to speak in more depth over. So, okay, Dan, if you could advance. So the planned and optimized scenarios, these are the ones that you might be most familiar with. So you've got Pete Irvine's one and David Keith's one of slowing the warming, Shepard's napkin diagram. As Alan was suggesting earlier, you've got impact orientated SRM. That might be ice cover, it might be crop yields, it might be any other variable that we might choose to use, heat stress. And then we've got cocktail geoengineering, the idea of being that we might look to try and balance the effects of geoengineering by having marine cloud lightning plus cirrus cloud thinning plus SAI, et cetera, et cetera, et cetera. Okay. Pete's desperately trying not to claim credit there for an idea that I've mentally attributed to him. Then you've got the emergency scenarios, tipping points, volcanic eruptions during the middle of your geoengineering deployment. Counter geoengineering is a fun one that Andy Parker, I think, has been discussing and doing some work on. And then you've got temporary termination. So if there's an interruption to deployment programs, again, I think Parker and Pete might have done some work on that as well. And then a technology switcher. So I think it's quite an important one where you might start, for example, with SAI and then realize that it doesn't work properly for whatever reason. You have to switch to, space mirrors or MCB or whatever. Okay, Dan. Then you've got the more regional interventions. You might look at doing something over the ocean, like the Great Barrier Reef experiments. You've got tropospheric aerosols over land, like you might use to ameliorate the Canada heat wave that everyone's so focused on at the moment. You've got single nation SAI. So you might have a situation where one country decides that they're only going to do it in one hemisphere, and it's everybody else's problem to work out the other hemisphere. Well, what if nobody else turns up and does the other hemisphere? How wrong might it go? Then you've got the polar scenario, which is that, similar to what David King and ICE 911 are advocating, that will give a different type of response. So you're really only concentrating on the poles. And then you've got the ground-based albedo enhancement on the poles as an alternative. And then the final classification, Dan, if you could skip. Oops, you've gone 2 slides. So the reactive global intervention. So you might try and really focus on reacting to sea level rise. So you might look to try and arrest ice sheet loss and endure temperatures that are potentially quite far below pre-industrial. And you might decide to cool below pre-industrial, as Kate Rickey suggested, to just benefit the economies of the hotter countries. So if we have a century where Nigeria and China turn out to be the largest players, then they might just prefer cooler temperatures. Maybe Europe and America become less significant, and the world agrees to have temperatures much lower than pre-industrial. What might that look like? And then we've got the kind of nightmare scenario, which is continued fossil fuel emissions with SRM. So I originally entitled that the burn everything scenario. We might not burn everything, but there might be continued fossil fuel use. We might hit some real limits with the renewable energy, and we might end up with a very, very high carbon atmosphere and SRM continuing. If you just skip to the last slide. So that's my contact details. Just as an aside, I do a lot of SciComm work. So I tweet as Geoengineering1, and I contribute extensively to the Google groups on both geoengineering and carbon dioxide removal. It's not about me and my views. I just share other people's science and other people's views without any commentary. And if people are interested in keeping up to speed on the field, I very much encourage them to follow those resources. We put a lot of effort and not an inconsequential amount of money into making sure that you guys are all kept up to speed. So please do take advantage of that. There's no cost for it. Just follow me and look on those groups and you'll learn a lot.
Thanks, Andrew.
Okay.
Ted.
Thanks, Andrew. That was great. Sort of a process question.
Dan, could I ask you to? Oh, actually, you might as well keep the sharing up because people will want to see the contact details.
Mm-hmm.
Sorry.
Yeah. 18 is a lot of scenarios. It's a lot of modeling time, and it's a lot of demands upon the attentions of people who consume scenarios. Have you thought at all about what process you envision for moving from 18 toward a smaller number? Is that something that will be an analytic exercise based on studies people do, or will that be kind of a response to the evolution of political and climatic reality?
Personally, my approach is to sort of throw as much mud at the wall and see what sticks. You know, people will look at this scenario and think, hey, that's easy or that's informative, and they'll do the bits that they like. You know, if someone were to ask me personally which ones I felt were most informative and important, then I could come up with a list, but I don't think that, you know, I necessarily need to be involved in that filtration process.
Simone?
I think the exercise for this paper was not to think about practicality of doing all the scenarios at once. It just was supposed to show the scope of possibilities, to really outline it, because people talk about all the scenarios, but it has never been really condensed in a paper. The goal is not to say we want to do them all. Well, maybe if somebody reads it and says we put a whole bunch of money into this and let people do all the scenarios, great, we know it's not possible, right, to do all the scenarios. That's why I think what your paper is doing on the scenarios is very valuable, to say, what do we actually want to focus on? This one was really just to say, there's this whole bunch of ideas out that people came up with in the last whatever years, you know.
But if the NASEM recommendations followed, and we do get $100 million for modeling and experimentation, then you will easily have the money to model most or all of those scenarios as part of a rational program of science. So I don't think it's silly to come up with a big list and then maybe we'll get the money to do it all.
But it also outlines how difficult it really is, because these scenarios cannot just be done. We can discuss it later. The models are not even ready to do many of them, you know, realistically.
No, we didn't focus on the, you know, my original intention was to go down to the sort of level that Doug was suggesting of you know, looking at that kind of detailed graphical level for each of these models. But the paper was just beyond the scope of the paper eventually to do that level of detail, and it, you know, that work can be picked up by other people.
Okay, we need to move on to the next, and we can always keep all of these discussions for later, of course. So now is Ted's turn.
Or Josh,
Or Josh?
Yeah,
I think
I'm doing the first 2 minutes and then turning it over to Josh, and I'll be managing the slides, advancing the slides for both. Slides visible?
Yes.
Yep.
Audible? Great.
Mhm.
Thanks. Greetings from beautiful and no longer 40 degrees Victoria, British Columbia. Greetings at 5:15 in the morning too, or whatever it is. I'm starting from the opposite end, but I see a lot of points of complementarity between what Josh and I are going to discuss and the prior two presentations. As solar geo becomes more prominent and contentious, which it already is and will continue to do as climate stress becomes bigger and more obvious, policymakers are going to be coming knocking to Earth system modelers and other scientists with questions. They won't do a good job of distinguishing what questions can and what questions cannot be answered by ESMs. And they're going to make decisions based upon scenarios that some people give to them that have to meet certain criteria of usefulness that are distinct from the criteria of usefulness for scenarios used in scientific settings. So generally speaking, the conditions for a useful scenario is that the conditions it portrays or something that looks similar enough to them are judged plausible enough that they merit the investment of time and attention for senior decision makers and bureaucratic enterprises to pay attention to them. Worry about, plan around. In addition, informative scenarios in policy settings, they have an analogous requirement to the requirement for high signal to noise in a scientific setting. There has to be a big enough difference, but it's a difference on a different set of dimensions. It's a difference on some aggregate assessment of, is this okay? Is this a desirable trajectory or an undesirable trajectory? And does it have different implications for what the apparatus of state decision-making should be? So the differences among scenarios have to be big, but they're not limited to differences in those system responses. And this is where you get some of the subtle margins of questions that come from policymakers that can or can't, or usually partly can be answered by ESMs. In addition, using Doug's term of strategy, the content of differences of scenarios to meet these criteria are very often going to include finer scale details that Doug and his colleagues moved aside into the characterization of strategy. It will be, what are the goals of the scenario, where the goals are not exclusively defined in terms of a univariate delta t. They will also include elements of what do you control in order to get that. And so what scenarios are useful are going to interact over time with advancing knowledge and technical capability that determines the changing answer to the question, how many knobs are there and how do they work and how do they interact? Andrew already made the point, scenarios should not be limited to sensible or desirable intervention pathways. And indeed, that's a challenge for organizations producing scenarios, but it really is the case. It's hard to articulate a bad scenario, but policymakers need bad scenarios. At the highest level, was that ding meaning I'm already at 5 minutes? 2 minutes?
No, you're at 3 minutes. You're now at
okay.
3.5 minutes.
The highest level questions that policymakers are going to pose parse into two. How much good can they do? How much bad can they do? They won't ask them in exactly those terms, but that's what they mean. Either form of those needs a bunch of additional specification, and there's a few examples of scenarios that might be useful under each of those. How much good first directs you to peak shaving scenarios, which are well known, have been extensively done. It also will direct policymakers to scenarios that are more active and interventionist. There won't be a clear boundary between things that undo harms and things that add additional benefits. So you can expect different forms of demands in that space. How much harm question? There's two forms that are salient in discussion. So people have extensively discussed excessive reliance scenarios. There's a suggestion and a discussion that I think can proceed about whether those are useful or whether, what's useful about them is so far in the future that it should be put off. The other form of bad scenarios are about regional or partial or targeted objectives short of global optimization. People have suggested things like Arctic sea ice, but a whole category unexplored is scenarios of deployment that are optimized for regional rather than global benefit. Josh is going to discuss a couple of examples of those.
Thanks, Ted. So yeah, let me try to go over this fairly quickly. So we're looking at a more specific example of one of these harmful scenarios that you can title unilateral deployment to maximize gains. This is based on our observation that one of the most basic scenarios that policymakers want to know about is very simply, what would happen if a major power, if a great power deployed SAI, I'll wrap it up very quickly, to optimize its climate, if it tried to maximize its gains only for itself and not for the rest of the world using SAI. There's a need to unpack some of this in terms of who would the major powers be, how do you think about that? Obvious candidates are the US or China, but it's difficult and problematic to explicitly model states like that. And states like this don't always correspond to the regions, Georgia regions or others that are typical in modeling. So one solution is to sort of combine different regions, for example, Eastern, Central, Western North America into a proxy for the US, similar for China with East Asia and Tibet. And then additionally, the question of optimization, well, obviously that's a tough question with no objective answer. It's about values and politics. We sort of would point towards an initial starting point of using the work done by Burke, Sheng, and Miguel in 2015, which identified 13 Celsius as what's optimal average temperature in terms of economic growth and welfare as maybe a starting point, not the final answer, but a good way to start. And then Ted, can you advance the next one, the last one? So let me say a few more words about this. This is what, again, what we call the maximized gain sample scenario. And this is what we're sort of proposing or would see a lot of value coming out of. In one scenario, North America, that is to say the US, seeks to stabilize annual average regional temperatures at 13 degrees Celsius, say within 20 years, maybe longer. That's up for discussion. Similarly, you could do the same thing with East Asia, China, seeking to stabilize its annual average regional temperatures at 13 degrees Celsius within 20 years or whatever time frame. The two questions then are, what are the global effects of these sort of bad, harmful, self-interested scenarios? And then to what extent do those effects differ from the effects that are produced from good scenario runs, from optimized sort of global welfare scenarios. Is it a big difference or a small difference? And that question, even though it's as highly simplified and unrealistic, would be very useful to policymakers at a very high level who want to answer some of these very basic questions to sort of establish boundaries about what they're working with. And so we would hope that something like this would have some appeal for the GeoMIP community. Obviously, we haven't got into great detail, but it's sort of, we've sketched out a scenario, and we're hoping that some folks find this intriguing. All right, thanks.
Thank you, Josh and Pat. I'll answer the question. Yep.
Are you suggesting that North America could control its temperature without controlling the temperature of all places at the same latitude, for example? I mean, that there's no way to do, we're less than 2% of the surface area of the world. We can't just control our climate. Right.
So we're not suggesting that. We're suggesting that in this sort of imaginary scenario, the US seeks to optimize its climate without regard to what that does for the rest of the world, which would clearly affect the rest of the world. It's, you know, across the board in terms of the latitude, certainly. So it's, to what extent would the global effects of that, which would extend far beyond what the US does for itself or wants to do for itself, you know, how would that play out? How would that compare to a coordinated, collaborative, global effort? Is there a big difference or a small difference?
Yeah, of course they can't do it, Alan. But the interesting question under the broader heading of like how much trouble can this make is suppose someone tried. What would they do in the pursuit of that effort, and what would the consequences be? And if the answer is you can't really do much that differentiates a one major region from the rest of the world, that's a really important result.
Sean, if you have a very brief question, otherwise you can just save it for later.
Very, very brief. So even just the question regarding there being a target that the United States should be looking at its own region just at 13 degrees. The unwritten following text is, and what about everything else? Because we know it will affect everybody else. Even the framing of the question, I would ask whether that's actually the right thing.
Well, yeah, I mean, I think it, of course, would affect everybody else. I think the question is, if policymakers want to know what's the worst that could happen, or what's one bad thing that could happen. What if a country didn't care about any of the rest of the world and just sought to help itself out of its own self-interest, and you know, just launched a program that tried to optimize its climate? Of course, that would affect everybody else too. So, to what extent would the global results of that differ from a more enlightened, sort of well-planned, globally collaborative deployment?
Yeah, okay, we need to move as well. Sorry, we need to move to the next talk because it's time.
Ted, could you stop sharing, please?
Yep. And it's Claudia's turn. So, Claudia, please take it away.
Yes. Do you see my slides?
Yep.
Yeah. We'll see your conclusions.
No, that's not the one I wanted to start with. Oh, come on. Yeah, sorry for that. Here we go. Yeah, it's the first time I do a presentation with Zoom. Yeah. So we played a bit with the climate economy model in which we integrated sulfate geoengineering, so SAI. We have a paper 2 years ago where we just added SAI to the DICE, Dynamic Integrated Climate and Economy Model, as DICE was, and then now we do ongoing work with changing a bit the energy model of DICE. So DICE basically works like this. You have an economic motor. So if you have capital and people, you can produce something, and what you produce, you can then consume or invest for new capital. And the more you consume, the happier you are. And the policymaker tries to optimize happiness integrated in time, so now and in the future. Unfortunately, if you produce something, you also emit CO2, which causes global warming and then damages your economy. So you can do CO2 abatements, that's emission reduction, which costs money, but you also reduce the climate damage. So then the policymaker would try to find a trajectory that optimizes happiness by balancing climate damage and abatement costs. So that's the model which we found. And maybe I should also say it's a global model. So we have one global region, which is homogeneous, and one decision maker. Yeah, and so the first thing we did was adding SAI. The details are in the longer slides, which are in the drive folder. But basically, SAI reduces global mean temperature. It can directly cause damage, but it can also cause, together with the CO2, residual warming like shifts in precipitation, which can also cause damage. And now we have two knobs to turn on, which is the amount of CO2 abatement and the amount of stratospheric aerosol injection. There's one catch in the DICE model, which is the way how the costs of abatement are computed. That's a very simple equation. The costs are some constant C0, but it's not constant, it changes in time, times the abatement to the power of 2.6. So the more abatement to do, the much more expensive it is. That makes sense. But this cost C0 does not depend on previous abatement efforts, which makes no sense at all, right? Because if I build a windmill this year, then it is still there next year to reduce my CO2. So the costs depend on what you did earlier. Okay, but for now, let's ignore this problem and just use DICE as is. Then this is what we got. So the blue line is the case when the policymaker does not have SAI, it can only do abatement. And the green line is where he can do both. And you see that he delays abatement by about 30 years if he also has the possibility of using SAI. And the SAI he uses is something equivalent to, say, 3 Pinatubo eruptions per year. So, but keep in mind that the abatement is delayed a lot, 30 years in the original DICE model. So what we did now, but it's still work in progress, is to replace this strange way of implementing abatement cost by a very simple energy model. So the policymaker has the choice of brown and green electricity plants. Brown plants are cheap to build, but they use fossil fuel and emit CO2. And green plants do not use fuel, but they are initially costly to build. But the construction costs decline the more you have already built. And this is the result we get. So the red line is where the policymaker completely ignores climate change. And you see that even then, eventually he will go to green plants because fossil fuels is getting too expensive. And the two blue lines are where the policymaker does take climate change into account and either can or cannot do SAI. And you see that the timing difference then between the green transition is very small. It's only 5 years. So if your abatement is more transition-like, that you have to go through it, you have to go from brown plants to green plants, but once it's done, it's done. Then the cost of the transition don't depend so much more on the timing, you just have to do it at some stage. So the option of SAI doesn't make it that much more attractive to wait. And you use much less SAI than in the previous. So, and the last thing which we do was to assume that we don't have one global model, but we have two competing regions. So the regions each have their own decision maker who try to optimize their own welfare. And they can either be fully altruistic, so try to optimize global welfare, or fully egoistic, so just looking for their own welfare. And we were interested in whether this egoistic behavior makes a bigger reliance on SAI. What the heck? Yes, here we go. And so here, up here, you see the altruistic and down the egoistic scenario. And you see a difference in the green transition. So if all are egoistic, then they're waiting longer because everybody hopes for the other country to start the transition and to, start building green plants so that they become cheaper for yourself. So everybody hopes that the other one will start the most difficult step. So that's why the abatement is delayed by 25 years. But still, the question of whether or not SAI is available makes quite little influence, at least in this scenario. But we are working on constructing more, for example, with having two regions that have different damage from SAI or different vulnerability to climate change. That's it.
Okay, great. Thank you, Claudia. Well, so I'll start with a question. Can I mute it? No. So in your model, what's the cost of it? So is there any cost related to SAI? And by cost, of course, I don't mean the actual cost of deployment, but more like the consideration about damages the same as climate change. So is there any consideration of, bad things that could, bad environmental impacts?
So
okay.
I didn't put a slide because I had so few time, but I have it in the longer slides. So what we did was, so okay, the original DICE model has a very simple damage function, which is goes with temperature squared with some constant, and it's very mild. So that's one of the many weaknesses of the DICE model. And what we did was first we split the temperature damage into a contribution from temperature, from CO2 concentrations, and from residual climate change, which we took to be global precipitation change for simplicity. So that's one channel how also SRI can influence this precipitation, therefore damage. And then we have a last term, which is the damage from the SRI itself. And for some basic scenario, we said that it is 20% as much as reducing the temperature change from 2.5 degree to 0. But as the original damage function, these parameters are quite arbitrary. We did a bit of sensitivity analysis, but in fact, it's impossible to get them right in some way.
Anybody else has a question? Okay, Adrian. Yeah, Adrian.
I originally had the same question, but I'll build on that. I'm just wondering, did you guys think about endogenous climate damages as in affecting economic growth itself rather than just capital?
We didn't do it. I mean, one could, but there is some coupling is there, because if this year I have less GDP, then I will invest less, then I have less capital. The next year I will have less GDP, not only from the damage next year, but also from the fact that I've invested less. But we didn't change that from DICE. And obviously, you know, DICE is only a testbed model. You cannot use it for more than very explorative basic studies. So obviously one could think of improving that.
So does this give us a quantification of moral hazard then?
Well, I mean, for now, I'm not sure if you can quantify it. So we wanted to see if there are parameter settings which are plausible, under which you have such a thing like, for one region, you still do a strong green transition, relatively little SAI, but for several regions, you start relying much more on SAI. So we want to explore the parameter space to see if we find, you know, a plausible setting where this happens.
Okay, thank you, Claudia.
And Claudia, could you stop sharing your screen, please?
Yes.
Thanks.
And now it's Pete's turn. Pete, you're a co-host already, so you can share your screen whenever you want.
Okay. You can hear me, right?
Yep.
Yes.
Great. Nope. Okay, and you can see my presentation now.
Yes.
Excellent. Okay, so I guess mine sort of, to some extent, is an antidote to the scenario focus. Is instead to think a little bit about, are there analysis approaches we could take that would reveal something about solar geoengineering that is sometimes hidden in our scenarios? So let's start by looking at the GeoMIP Geo1 experiment, the classic. We could arrive at what I call a conditional scenario-dependent claim that we're quite familiar with. If we restore temperatures with solar geoengineering, we weaken the global mean hydrological cycle. And here I've shown the temperature result, the precipitation result. You can see a 6.9% increase under 4 times CO2 turns into a 4.5% decrease under G1, relative control. This is illustrated here on the left. Got a laser pointer. There we go. Now, what I'm suggesting is we could shift from a conditional scenario-dependent claim to an unconditional efficacy claim, where we say solar geoengineering is more effective at offsetting global mean hydrological change than emissions cuts per degree Celsius global warming offset. And what I do here is I flip solar geoengineering around the other way, so that where it opposes climate change, it's my efficacy. It's basically just get the numbers the right way around. Divide the effects of solar geoengineering by the effects of climate change, and find that it's 165% as effective at offsetting hydrological change than emissions cuts are. Now, this works well for scenarios where we've offset all warming, but of course, all of our scenarios, we offset a different amount of warming, and we look at different baselines, blah, blah, blah. If we normalize by the temperature effect, so per degree Celsius warming offset, we've now got a metric that we can apply across all of our different geoengineering scenarios. And that's what I hoped to do for this meeting, but didn't have time to do. So I'm just doing a little illustration of an application of this idea to the UKSM results for G6 sulfur and SSP 585. Now, G6 sulfur goes down to SSP 245, but what I wanted to know is it more effective per degree Celsius offset than climate change? So here I'm sorting my precipitation results on the basis of the SSP 585 anomaly from the most negative anomaly over here. So the Pleistocene, the driest, biggest reductions in rainfall on the far left, through 0, so no change, and then off to the largest positive changes on the right. And then I've binned the G6 sulfur results into those percentiles. And that's shown in blue. So you can see the spread of the G6 sulfur response against the SSP 585 response. And you can see that, broadly speaking, the effects of G6 sulfur are equal to and opposite to those of SSP 585 when you have large positive anomalies. As your anomaly gets smaller and smaller and smaller, it starts to become more effective. You've got about a doubling of the effect of SSP 585. And then at burn 0, you got whatever. And then on this side, it's similarly quite effective. So we add a few more lines. These red dashed lines are now showing you where, if you offset all warming with solar geoengineering, you would result in an increase in the magnitude of change. So you go from, if you go above this red line, you go from 5% to -6%, because geoengineering is more than double the size. And if you go below this line, you've gone from 5% to +6%. So you're adding to the effects of climate change if you fall below that line down here. So what I'm hoping to do is plug not just one model in and not just one variable, but grab as many models and experiments as I can and crunch it up so that I sort of break it into different zones, like where the effects of climate change are largest, what does solar geoengineering do? And looking at this, we can see that basically it's highly effective, basically does exactly the opposite of what climate change did in those regions where the effects of climate change are large and significant. Where they're a bit smaller but still significant, you can see that it tends to be a bit over-effective. And where it's insignificant, you can see that in some fraction of places it does increase the magnitude of change, but there wasn't much change to begin with. What I want to do is test that in other models, test it in multiple experiments. So this is more of an advert. Who's interested in helping out do a meta-analysis of stratospheric aerosol geoengineering? I think this normalized efficacy framework will allow different stratospheric aerosol geoengineering experiments, G3, G4, G6, blah, 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 to be compared on a consistent basis. And I think by doing some clever sorting, we can arrive at some, what I think would be really robust policy relevant claims, such as where the effects of climate change are greatest, the upper half of significant changes, stratospheric aerosol geoengineering will be highly effective at offsetting those changes and will effectively not make any of them worse. If you're interested and have some data to share, give me an email. If you'd like to use the code, it's a prototype at the minute, but if you'd like to use some of this code or some of the stuff I was using in my half and warming paper, give me a shout, because I haven't made it that accessible. But if people are interested, I can make it more useful and put it up on GitHub. Thanks for listening.
Thank you, Pete. Jim has a question.
Yeah, it's sort of quite an interesting idea. I mean, you know, normalizing stuff per degree of warming or normalizing per injection amount or per optical depth is something that is relatively frequently done. But the problems normally come from non-linearities, and you know, there's some large non-linearities that you've got, particularly on things like stratospheric aerosol injection, where you've got a reduced efficacy in terms of well, pretty much everything, stratospheric aerosol optical depth, cooling, etc. So how do you deal with that? Because then obviously you've got this sliding scale. So it's not per the Kelvin don't relate necessarily to the SO2 injection.
Yeah. Yes. I guess what I would say is we're currently not drawing as much information as we can from our existing simulations because of these issues. I mean, I think to a large extent, the climate response is pretty linear. And I think if we ignore the fact that it's pretty linear, we're actually kind of throwing away a lot more information. And now, I think you're right. Of course, certain things like, say, sea ice extent is very nonlinear. Like RCP 8.5 will wipe it all out. And so that isn't going to go linearly. And yes, you're right. I think the aerosol forcing and some of the consequences in the stratosphere won't be quite linear. That's obviously something that this is not like a solve everything solution, but I think this approach can reveal certain things and it can allow us to compare different scenarios. And well, I mean, we're able to test just how linear it is. I mean, you could repeat the same analysis I use 2070 to 2100, you could do the same thing for 2040 to 2070 and see if the results differ much. They might, but I imagine the broad, grand scale picture of where the effects of climate change are biggest, you're certain to reduce them, is going to be robust. But yeah, it's definitely nonlinearities, and this isn't a universal solution.
Okay, any other questions?
And if anyone's getting deja vu, I did present this 2 years ago, or the beginnings of this idea 2 years ago. So it's not just you. Well, if no one's, I'll show you a slightly. If no one's got any questions, I might show you a flipped version. So this is the same thing, but now I'm dividing by the effects of solar the effects of RCP 8.5. So now, if solar geoengineering is perfectly effective, it falls along this one line here. And if it's between those two red lines, then it's reduced the overall magnitude of change. And so you can see that for, yeah, it obviously has a discontinuity at 0 because you divide by 0. But you can see here my statistical significance tests also sort of diverge up. So you can see that almost all the points land between those two. But for precipitation, there is a definite feature of being over effective at offsetting change. So there's places where you go from plus 5% to minus 5% if you offset all warming. That's quite a different character of behavior from adding to the effects of climate change, which is where you go below this line down here. And I think that's something we've really not been good at communicating, is distinguishing between where solar geoengineering actually makes things worse no matter how much you do, so where it adds to the effects of climate change, and where it might make things worse if you happen to do too much of it, which is would better characterize the points that fall up here. This is totally avoidable if you say offset half the warming. You, instead of going from plus 5% to minus 5%, you can go from plus 5% to 0%. So yeah, I think we really need to, I think that this is an important thing to communicate, and I hope that this tool would be useful for doing so.
Awesome. Thank you, Pete.
Cool.
We can move to the last talk for today, which is from Ross, and it's going to be a little bit different from all the others. So take it away, Ross.
Thank you. Is my screen showing here?
Yes. Okay. Yeah. Now it's sharing. Yeah.
Okay. Great. Let me know if you're seeing presenter view instead of title slide. Okay. So thanks for having me. I am with the Planetary Sunshade Foundation, which is a new organization organizing space-based geoengineering community. We spun out of the Center for Space Resources at the Colorado School of Mines and have sort of accumulated a group of collaborators throughout the United States and in Europe. So what we're working on is to try to develop the concept of space-based solar geo. I'm sure most of you have heard of it. It's an old concept, generally regarded as infeasible, out of hand. But we think, or we've noticed from the aerospace community with the advent of Starship and the renewed interest in space mining as part of the Artemis program and other sustainable human exploration projects, that it looks like it might be feasible around the middle of this century to actually create planetary sunshades at L1. So how do they fit into the solar geoengineering technology portfolio? We think they're complementary to atmospheric geo. Sort of the short story of it is that atmospheric geo is fast, dirty, and cheap. That's dirty in the public mind. I think it's a lot better than the rep it's given, but that's where we're at politically. Space-based, the obvious advantage of it is it's outside the atmosphere. So it's slow, clean, and expensive. These L1 flyers could last for centuries and could support a sustained intervention. There's also positive externalities, which is something that my community is excited about. Essentially, if we can build this in space, we can build anything. And that's something that we're, to be honest, trying to look for a reason to do. But we also think that we're heading to a world in the next 20 years where geoengineering is going to become very salient to everybody. So here's how planetary sunshades work. For a little refresher on that, they orbit at Sun Earth Lagrange 1. It's a stationary point in the Earth-Sun reference frame where you can just stay between the Earth and the Sun. You need about 1 million square kilometers for 1 degree of cooling, but you can make things very, very thin in space. So the mass comes out to on the order of 100 megatons. Obviously, that's much larger than anything we've built. The International Space Station is 0.5 kiloton, but this project is predicated on an assumption that access to space in the future will not be like what it has been in the past. And I'll talk about two branches of that sort of at the end. One thing that I think is interesting for the GeoMIP community is that a planetary sunshade could be spectrally selective. So it could be possible to independently control the hydrological cycle and global temperatures if you made a sunshade that was either refractively or absorptively spectrally selective. Oh, and on the bottom right here is a picture of NASA's solar cruiser. This is a solar sail that's going to launch in 2025. It's a technology demonstrator to demonstrate station keeping at Lagrange 1. And that is run by NASA for different reasons, but the PI has been working on planetary sunshade research in his spare time for the last 20 years. So here's the concept history of it. It was first proposed by James Early 1 year after Hansen testified to the Senate. I think it got probably more attention than atmospheric geo for some time before it was sort of finally kind of put down and retired around 2006, which is when Roger Angel put together a NASA Advanced Innovative Concept Study that basically came up with an infeasible launch system. Recently, it's been picked up. In the meantime, before that, Sanchez and McInnes had some interesting results that I think you shall be aware of, and I'll show on the next slide. We started doing the conference circuit and talking to the aerospace community about how this might be possible with the Starship and space mining. And we've got 2 master's theses out of Stuttgart. We have a new paper out of KTH in Sweden, and there's a consortium being led by OHB in Bremen. So sort of a lot of European work on developing the flyer architecture. And we're spinning up a sort of center of excellence at the Colorado School of Mines for doing large scale space resource architectures for making this thing out of in situ resources. Here's the results from Sanchez and McInnes 2015. It is sort of a control optimization of a sunshade. The top right is moving out of plane to latitudinally control shading biased towards the poles. The bottom right is residuals in a simple GREB climate model run on a laptop. Right now, there is a master's student and a team of 10 undergrads working on updating this with a new control law for a more disaggregated sunshade concept and new climate models. Would love to sort of connect you with them if anybody wants to reach out. Okay, so why is this idea not crazy? What are we tapping into? Because I think we all understand that the space mirrors could be a great idea if we could build it. The question is, can we build it? The Mars fleet that SpaceX is proposing to build is architected to put 1 megaton of materials on the surface of Mars in 20 years. And the catch is that they can only launch those ships every 2 years. So you can launch ships to the moon anytime in between those windows. So if you baseline an architecture that puts that same 1 megaton of resources on the moon instead of on Mars, you can build a space mining architecture with 100-to-1 mass leverage and construct the material resources to construct a sunshade in deep space in those same 20 years. So it's kind of coasting on that. Pitching it to space agencies, pitched this to the chief scientist of NASA. He's super excited. He's very, it's obviously far out for them, but NASA has invested in Starship as their primary moon lander. So this thing on the right is this giant moon lander they're going to build, and SpaceX is promising to build 1,000 of these ships. It ties into everything NASA is doing in terms of ISRU and trying to make a sustainable human development in space. It's plausible that the planetary defense mission could be extended to include climate change, not just asteroids in the face of catastrophe. And lastly, we did a really unscientific, unpublishable poll, but we just sort of spun it as well as we could and asked people if they'd rather see a space-based solution to climate change or a city on Mars. And it was 7-3 in favor of a space-based solution to climate change. So we think as the increasing salience of climate change compounds, that we have an opportunity to build something here. So I'd love to speak further with any of you. We have regular meetings Thursdays at 11:30 Eastern. I'd love to invite you. You can reach out to me at ross@planetarysunshade.org.
Great. Thank you, Ross. Simone has a question.
Yeah, so if I understand, it's an amazing concept, obviously, and that you're actually trying to work on that. So it seems like you're saying that you can dim the sun dependent on latitude. So you could overcool, cool more the high latitudes, but you also said you could control precipitation because temperature was changing the spectral I guess, Jimmy. How do you do that? I don't understand that.
We've been a preprint has been brought to our attention that is called a radiative antidote to CO2. And if you control the long wave versus short wave ratio, you can theoretically control cooling at the tropopause, I think. This is getting a little out of my realm of comfort, but that seems to be a plausible means of manipulating the hydrological cycle independent of global temperatures.
Yeah, okay, yeah, okay, thanks.
Adrian?
Yeah, just really quickly, any thoughts on space debris? Would this kind of solution be resilient to that, and how would you approach it? Is it a problem?
So you want to build it at Center Earth Lagrange 1, which is 4 times farther away than the moon. It's obviously very large. There will be debris created. It will have to be collected and managed. Most of that debris will not end up in the low Earth orbit system, where the Kessler syndrome is a factor, and that's one reason to not deploy low Earth orbit sunshades. There are some zero energy returns back to Earth, so that needs to be modeled and better studied. But those, at least at the L1, the space debris will be moving at low velocity relative to everything else, so you're not going to be having an exponential increase in it.
Ross, could you put your contact details, and the details of the meeting that you're promoting in the chat so that people can follow up?
Certainly.
And I guess, so I have a question. When you have these pretty large space mirrors, right? So have the risk of like solar flares been considered? Wouldn't that have a huge amount of ram pressure from the solar winds, and would that knock them out?
Yes.
L1?
That is being considered. It hasn't been formally studied, but a really big Carrington event style thing could disrupt the sunshade, and that's one of the reasons why atmospheric geo is a complementary technology. The sunshade can serve as a wind down technology for atmospheric geo, but atmospheric geo can serve as a backstop for the sunshade. But smaller solar flares could be handled with smaller sunshade flyers. This thing would be we haven't really determined what the upper size for an individual element is, but the aggregate size of the swarm is what matters.
Okay, thank you. So we will stop here for a break and